everyone, my name is Tamsin and welcome to this workshop on electric circuits. I'm excited to be working with you today and let's jump right in. So first, let's go back to the basics. Remember that potential difference is denoted by V and it's measured in volts. It is the work done per unit of positive charge, and here's the equation that we use when working with it. Next is current, denoted by I. It is measured in amperes and it is the rate of flow of charge. This is the equation that we use when working with it. Next is resistance, denoted by R, and we measure this in ohms. Resistance is a material's opposition to the flow of electric charge. So let's look at some of the instruments that we use when measuring these. Potential difference is measured by a voltmeter, and this is always connected in parallel. This is because it has a very high resistance, and so virtually no current passes through it, and this would interfere with our circuit. Next is current, which we measure with an ammeter, and an ammeter is always connected in series. This is because it has a very low resistance, as current does not slow down when passing through it. Next, let's look at Ohms Law. So Ohms Law is the current through a conductor is directly proportional to the potential difference across its ends, provided that the temperature remains constant. This is the equation that we use when we deal with Ohms Law. And if we look at the graph below, we can see that V is directly proportional to I. That symbol over there is called a rheostat, and a rheostat changes resistance. This changes the current, and thus the current through R. We can then measure the potential difference across R and plot the relationship on a graph like we just saw. So conductors can either be ohmic or non-ohmic, and ohmic conductors obey Ohm's law, and so in this graph we can see that V is directly proportional to I. And then non-ohmic conductors do not obey Ohm's law, as we can see in this graph. So let's take a look at an example. For question A, it asks us to find the total resistance. So we know that the total resistance in series is equals to R1 plus R2 plus R3. R1 plus R2 plus R3. So that would be equals to 4 ohms plus 6 ohms plus, that's a 6, plus 12 ohms. And that gives us a total of 22 ohms. And that's question A. Then if we move on to B, it now asks us to find the reading on ammeter A1. So we know that I, which is current, is equals to V over R. And now we're going to be working with the totals. So the total voltage over the series circuit is then 44 volts divided by R, and we've just worked out the total resistance, which was 22 ohms. And 44 divided by 22 is 2 amps. And this is going to be the same in between all of the resistors. Now let's move on to question C. Let's just erase this. So question C now asks us to find the readings on V1, V2, and V3. So we know that V is equals to IR. So if we're looking at the first voltmeter, we said the current is going to be consistent through all of them, and we've just worked out in question B that the current is 2 amps. We times this by the resistance, which would be 4 ohms, and that gives us a total of 8 volts flowing through voltmeter 1. If we do voltmeter 2, again we know that voltage is equals to I times R. The current is still 2 amps, and now the resistance is 6 ohms. This then gives us 12 volts. For voltmeter 3, again, I times R is equals to V. Current is still the same, and resistance is 12 ohms, which then gives us 24 volts. Now let's look at parallel circuits. The resistors are termed current dividers, and again, we'll have a look why. So the current going into this parallel connection is equals to the current going out of this parallel connection, which means that A4 is going to be equals to A5, which is equals to the sum of A1 plus A2 plus A3. If we now look at the voltage, the total voltage over this parallel connection is equals to the voltage over the first branch, which is equals to the voltage over the second branch, which is also equals to the voltage over the third branch. This is just showing what I said. So let's take a look at another example. A asks us to find the effective resistance of the parallel connection. Well, we know that 1 over R parallel is equals to 1 over the resistance in the first branch plus the resistance in the second branch plus 1 over the resistance in the third branch. So this would be equals to 1 over the 2 ohms in the first branch plus 1 over the 1 plus 5 ohms, which is running through the second branch, plus the 1 over the 4 ohms, which is running through the third branch. If we total this up, we get 1 over R parallel is equals to 11 over 12 ohms. But now we are looking for the resistance parallel, not 1 over the resistance parallel, so we've got to flip both of our fractions. So we can get R parallel is equals to 12 over 11 ohms, which if we work that out, we get 1.09 ohms. And that's question A finished. So let's move on to B. B now asks us to find the reading on voltmeter 1. Well, we know that V is equals to I times by R. And we're going to have to work with the totals here. So the total current we can see is 3 amps. This is before the current all splits through the different branches. So let's write 3 amps times by the resistance. So the total resistance in parallel we just worked out, and it worked out to be 1.09 ohms. If we work this out, it then gives us 3.27 volts. And that is the reading on voltmeter 1. Let's do C. C asks us to find the reading on ammeter 1. Well, we know that in a parallel circuit, the voltage, the total voltage is equals to the voltage over the first branch, which is equals to the voltage over the second branch, which is also equals to the voltage over the third branch. So we know that this voltage over here, if I draw it in, is also going to be equals to V1, which we've just worked out in the previous question is 3.27 volts. So once we know this, we can use it to calculate I, as I is equals to V over R. So I said that the voltage is equals to 3.27 volts. Resistance in that branch is equals to 6 ohms. And if we work that out, it works out to be 0.545 amps. And so that is the reading on A1, which is the current running through the middle branch. If we then move on to D, let's erase this. It asks us to find the potential difference across the 1 ohm resistor. Right, so the 1 ohm resistor is this one in the middle branch. So we know that V is equals to IR. And we just worked out that the current flowing through this branch was 0.545 amps times by the resistance, which they've given us is 1 ohm. And this gives us 0.545 volts, which is then question D complete. This is an example that you're going to try by yourself, and in this example, the resistance of the cells and the connecting wires can be ignored. So it asks you to please find the current through the 4 ohm resistor. So pause the video and give this a try. Well done on giving that a try. Now let's look at the answer. So if we're looking at the 6 ohm resistor, we can work out the current flowing through it. So we know that the current is equals to V over R, and they've given us a voltage of 2 volts and a resistance of 6 ohms. So that works out to be 0.33 amps. This is what is flowing through the 6 ohm resistor as well as through the 8 ohm resistor. We can therefore work out the voltage over the second branch. So we can say that V is equals to IR, and we've just worked out that the current is 0.33 amps, times by the resistance in that branch, which is then 8 plus 6, which gives us 14 ohms. And if we work that out, that gives us 4.62 volts. And because this is a parallel circuit, we know that the voltage through the first branch is equal to the voltage in the second branch. This means that the voltage over the 4 ohm resistor is also equals to 4.62 volts. And now we can use that information to work out the current that's flowing through the 4 ohm resistor. Let's clear the screen. Right, so the current is equals to V over R. And we've just said that the voltage is then equals to 4.62 volts. The resistance is 4 ohms. And if we work that out, that gives us 1.155 amps. And that is the answer to this question. So now let's take a look at some facts about parallel connections. Adding another branch to a parallel connection will always decrease the total resistance in parallel, whilst removing a branch from a parallel connection will always increase the resistance in parallel. So if we take a look at this picture, you can see how the resistance in parallel when the switch is open will always be greater than the resistance in parallel when the switch is closed.